thing that got me into paravane stabilization and paravane sailing was a competition 25 years ago called The Race around the world. And it was very open. It was no limitations on the sailing craft. And then I kind of invented the concept of sailing with a blimp and put some wings on it. That was before I got access to the internet. But when I got access to the internet, I learned that several others had invented that before, and even Stéphane Rousseau had made it in the real world with a paravane and blimp. But that was what I was thinking about, and the reason to have a paravane in the water and a blimp in the air is not only that it looks spectacular and or people think it's crazy. The reason is that it's much more efficient than having a hull in the water, because you have the volume and therefore displacement of the blimp scales with the length in cube, while the surface area or wetted surface scales with the length squared. So if you make something that is, or if you have a lower density, you will get much. You will get something that has lower drag for the same flotation force. So this made me start developing paravanes. Here you see this as I thought it should be, a blimp in the air floating and lined to a paravane. And as the interesting parts of the paravane is below the water, you don't see so much of it. But I, after doing this, coming up with this idea, I contacted Goran Marstrom, world leading tornado builder and very skilled catamaran sailor, and my friend Jens Osterlund, who was also active in the Trampofoil project. And Göran wanted, or he told that, can't you use these paravanes to sail 50 knots? And we decided to make a speed record attempt instead, because it was easier to make something, some kind of hull, and light hull and a wing sail and stabilize it. So and this is from the roll out of the speed sailing craft some 20 years ago. You see the speed sailing craft behind us, and here is a picture when it's sailing, and you can see the wing sail. Here it's an 11-meter high wing sail, and you have the craft foot here from the wing or the sail to the paravane, that is some 20 meters to windward of the hull. Here is it's a planing hull, and we have a bowsprit with a planing skid in the front to get longitudinal stability. And here I'm sailing at some 34 knots or something, and it's quite bumpy water. It was really choppy that day, and it was a quite open spot of water and quite deep water. And it worked perfectly, but this day I actually delaminated the hull. So the future testing we did at somewhat flatter water, but it worked quite well. but we never made 50 knots. We made several runs between 30 and 40 knots, but well, I think we never got wind that was steady enough. We had gusts that were above 20 knots, but well, so we've never made any speed record. When you're sailing this kind of craft, you have a paravane, or the paravane that I developed had you set it at a certain angle of attack, or you have a stabilizer on the paravane, so it gets a certain angle of attack, and you have a fixed angle of attack on the sail. And that means that you set the craft actually at the ratio between lift coefficient on the paravane and lift coefficient on the sail, and that means that you get a certain ratio between apparent wind and boat speed. And well, then the craft will assume a course depending on what such ratio you have. And if you want to control the craft, you change if you have a fixed angle of attack on the paravane, you have to change the angle of attack of the sail, and that way you can control the course. We actually had a small rudder on the Speed Sailer, but that was only used below 20 knots. As soon as I passed with 20 knots, I retracted the rudder, or it actually just let it go. So about 20 knots, the craft was controlled by controlling the sail. And when we designed the craft, we expected sailing somewhere between 3 and 4 times the wind speed would be somewhere here in the plot. If you have true wind here, boat speed there, and apparent wind there. But from wind measurements and speed measurements, we were more in this range somewhere here. And here is a picture of the speed sailing paravane that we made. We have a main wing here. This water surface is somewhere here, and we have a tether in a crowfoot arrangement. So we have this part of the tether is below the water surface. So we have the water line is somewhere here, and this part of the tether that is maybe a little hard to see is above the water all the time. And here is stabilizer that controls the angle of attack. It's and it is a little displaced beside the wake from the main foil, and that's because the main foil is trailing edge ventilated, so it has or base ventilated, so it has a hydrofoil section with quite thick trailing edge. So we have a ventilation bubble behind the main foil, and therefore the stabilizer has to be outside that wake. And here is what I call altitude stabilizer that as it says, controls the altitude of the paravane. And this is obtained by getting a downward force from the lift on the main foil and the tether. I will show that later. And because this altitude stabilizer is behind, a little behind the main foil, we get a downward movement, so this surface sensor is planing on the water and has a small lift force. If we go on here, here is the front view of the paravane with, let me see where I have the cursor, there it is. And here you see the main foil lift that goes a little downward, and the tether for the sail force that acts on the tether that goes in that direction. And as you see, it's a small angle between these two forces, and that results in a downward force that allows this kind of altitude control. And here you see a well, kind of perspective sketch where I have tried to illustrate the forces with the lift of the main foil, and the lift on this altitude stabilizer and the surface sensor that is necessary to balance this downforce. And the reason I put the altitude stabilizer quite near the main foil is that I want to have the force, the lift force on the surface sensor much smaller than the forces on the altitude stabilizer, since a planing surface on the water on the water surface is not as efficient as a hydrofoil. So the lift of on the surface sensor is just maybe a quarter or something of the lift on this altitude stabilizer, and these two forces together is about 1/10 of the main foil lift. So it's the lift on the surface sensor is just well, a few percent of the total force on the paravane. Actually, I thought I invented this, but as I got access to AYRS papers, I found that Paul Ashford did something very similar about 10 years before me. But it didn't look exactly the same as this, but the principle, how to keep altitude and control altitude is very similar to what I tried to explain here. Try to switch. And here is a side view of the same. It's maybe you see a little more clear the how the position of the stabilizers are well, relative to the main foil. And another, there are actually many issues here. And one issue is that you get velocity gradients in the water when you sail in waves. And therefore, it's an advantage if you can have the lift force from the main foil always acting through the same point. And therefore, I built the main foil so it lies on an arc around a point that is just above where the crowfoot from the tether come together here, and this way I always get the same angle between the sail force on the tether and the lift force from the hydrodynamic lift force from the main foil, and this makes the paravane less sensitive to velocity gradients. I try to show this on this image. Here is what happens if you sail in quite choppy waves. You get the velocity gradient in the wave because you have different particle velocity and different different depth in the wave. And then you can get a lift distribution that is maybe a little asymmetric, like this one, maybe a little exaggerated here, but here and here you have all the lift is displaced from the center of the paravane. You get the same downward force from the main foil lift and the sail force. And similarly, if you have lift distribution like this, and this situation can also occur if you have if you get ventilation in the surface piercing part, which is quite likely to occur. When that happens, you just get you can go on and it's not a very big problem. But anyway, this paravane, because it's not dependent on having very much lift where it's surface piercing here, it's not very dependent on that. So it's designed to have quite small lift coefficient or surface loading here in the surface piercing part. Here is the hydrofoil section for the main foil, or this was 20 years ago, and I switched computers sometimes between that, so I actually have to make a kind of reconstruction. But this is very much like the hydrofoil section we were using. And as you can see here, here's a profile contour. It's base ventilated, and the upper surface is some 20% shorter than the lower surface. And that's because when you have a ventilation bubble here, at high speed, the base pressure in the ventilated cavity you get here is quite close to the free stream pressure beside the hydrofoil or behind the hydrofoil. But at low speed, you get in real pressure you have the same difference, but in pressure coefficient it's a much larger difference, and that makes this hydrofoil or this part of the hydrofoil work as a flap. So you get higher lift coefficient at lower speed or very low speed, and that helps actually when launching the paravane and starting sailing. But at high speed you get quite constant lift coefficient, and at top speed it should be 0.14. That's design condition, but it can of course vary, and so it works. Say at when sailing at 60 knot speed, it will work at lift coefficient up to 0.18. That was about. And here is a testing that we made we were towing the paravane beside a large rib. Our intention was to go at more than 40 knots, but when we came up to 43 knots, the boat started to dance. So it couldn't, because the side force from the paravane was too big. So we could we had to do the testing at speeds up to 40 knots. The paravane was designed to, or is designed to work at 60 knots, but we could only go. And here you see, it's a lot of noise here, but here you see when we start here, it's just some 20 or 25 knots, I think, but we will increase the speed soon. So it's and here we are measuring the lift to drag ratio. We have a well, here is a measurement computer that's Jens set up. Now it's 30 knots now, but we will increase the speed soon to just below 40 knots. Here you see the device we use to measure the drag angle. It's a fin on a carbon fiber rod, and rotary potentiometer. There's 37 knots and 4.6 kilonewtons. You can, if you look at the paravane when we have it in a picture, you can see the ventilation bubble, and in this movie the ventilation bubble is actually a little too short. Well, should have edited this, but well, that's the way it is. Okay, maybe I shall well. Here we have two images, and the first image here, the top image, you can, if you look closely, you can see that the ventilation bubble here is quite short, and that is because the air supply was too low to the ventilation bubble. Maybe I should have told the reason that I chose this kind of base ventilated section, and that's because you can make something that is thicker with the same pressure distribution without getting cavitation. So it's when you go at high speed, it's a quite big advantage. I think Sail Rocket used something quite similar to this one, the hydrofoil section. But here, the ventilation bubble is too short. We actually measured the pressure in the ventilation bubble as well, and found it was the pressure was very low. So we had a substantial pressure drag on the hydrofoil section, and the lift to drag ratio was just 4.5. Here you see the tether as well, and you can see that it's it's ventilated in the part closest to water surface. That's intended because I actually made a base ventilated section on the tether on the surface piercing part, but from that point and downwards, it's a sharp trailing edge on the tether. And here, the lower picture, we have modified the paravane and made the trailing edge thicker in the surface piercing part, and also made a little better air supply through the fuselage where the altitude control stabilizer is attached. So it's and this made a substantial reduction in drag. So it was we got a lift to drag ratio at 5.5, corresponding to some 40% reduction in profile drag on the main foil. Well, if we go on with the tether, that is something quite tricky that I think most who have tried to make such or similar tethers have seen. But here is a section of the tether that we use for the speed sailing paravane. It is 45 millimeter cord. It has a very sharp, some 6-degree, I think, trailing edge angle. And the front part here is unidirectional high-strength carbon fiber laminate, and the rest is just epoxy with a very thin layer of glass fiber on the surface. The thickness is some 6.5%. And the reason it's so thin is that this is about the thickness you can make on a foil and not get cavitation at 60 knots speed. So as you see here, it's if you make a foil with sharp trailing edge, you have to make it quite thin. The main foil hydrofoil section was much thicker and had was still not cavitating at 60 knots. And the reason to make this a very sharp trailing edge angle is that if you have a more blunt trailing edge angle, a little wider angle, you will if you get a small disturbance in angle of attack, the lift you get then will act longer forwards. It will not act in the quarter chord point. It will act in front of the quarter chord point, and then it's a risk that it's no longer any stable. But there are some more problems when you make this kind of tether. And here's a view of how the tether looks like from above. It's built in an arc with some 10 meters radius, and that's because if you make it curved this way, you when you always have some drag on this kind of streamlined thing that you tow through the water, and that drag force will try to bend the tether backwards like this, and if you take, for example, a straight section and try to use it as a tether, this bending backwards will make the tension in the rear part higher. So the force that or tension stress that acts in the tether will act behind the center of pressure at the small angle of attack, and then it will become unstable. But if you make it pre-bent like this, it will become stable. Actually, I held a patent on this some 20 years ago, but it has expired since long, so it's not valid anymore. Well, here is an attempt to illustrate the problem. If you have or this is a problem if you have say that you have a small deflection in camber on the tether, then it will try to turn away, and it will assume it will assume a deflection where you have a where you have or it will get an angle of attack, so you get a lift, and that lift will, because of the bending or the camber, the lift will act in front of the quarter chord point where the lift should act if you had no camber at all. So therefore, it's necessary to have the center of stress in the tether well in front of this quarter chord point. And for the speed sailing application, this was actually quite critical. I tried to determine this and found that the maximum camber without getting too much lift force on the tether was just 0.03 millimeters. And well, if we can go back to well, some of these early sketches and to try to make this clear. If the tether in this configuration get the lift, the altitude control will no longer work, because then if the lift is directed upward from the tether, the downward force from the main foil lift and the sail force is not enough to get any forces on the horizontal stabilizer here, or the altitude control stabilizer and the surface sensor. So then if that occurs, the paravane will jump up through the water. From water. So it's and here, yeah, here is that. Now I should it's a quite small room I have, but it is here anyway. So here you see the main foil. Here you see the well, altitude control stabilizer, and the tether is here. So well, the room is unfortunately too small to make very much of this, but that was paravane, the one-way paravane. It's when you sail with the paravane, you have to start sailing and you have to stop sailing, and that can be a little tricky. For example, and you can have different strategies. You can make tacking or maybe not tacking, but shunting or jibing paravane. But you can also make shift paravanes when you tack, and that depends. What is best depends on how frequently you have to tack. But when you launch a paravane, the technique with this kind of paravane is that you take the paravane and you throw it in the water with the suction side down, and then it will start moving towards the screen like this, and then that is to windward, and then it will assume the right sailing position. And for retraction of the paravane, if it is a big paravane or a paravane with lots of force, it's quite difficult just to pull it in. But you can have a control line, so you pull the upper part of the crow foot here, and then it will flip out of the water and lay itself on the water surface and be quite passive, and then it's easy to pull in. So that's a way to shift paravanes if you want to do that. But you can also make, or I have tried. You can do lots of things, but I have tried shunting paravane design, and here's a model of that. Many of you have probably seen it on YouTube clip on the internet where I'm making a tack with this kind of shunting paravane. This one is actually works actually the same way as the speed sailing paravane. You have a main foil here. It's symmetric forwards, backwards, and you have this surface sensor can flip. So you have one active surface sensor in front, and you have this crowfoot arrangement, so you get the downward force, and you have a altitude control stabilizer here, and you have a angle of attack control stabilizer there. And when you go that direction, you have you control this stabilizer, and when you shunt, you use the controls so you shift this stabilizer to that position, and then it will shunt and go the other direction. So that's and that's the most reliable thing I have tried. I've tried other things, but it's those things have flipped out the water some way.